approximating the binomial distribution with the normal distribution. So the binomial distribution is based on, I guess, the discrete random variable. So if you recall, so we have a certain number of trials, okay, so the trials are independent, where there's really just two possible outcomes, either a success or a failure that we have. Now, the success happens with some probability p, okay, so that's what you see right there. And it is the same in every single trial. Now, as I mentioned, so the random variable is the number of successes that we have in a given trial. So that's what we have. Now, I have gone over this, and I'm going to make the assumption that you are comfortable with the binomial distribution. So the kind of, function or the probability distribution for it, with x being the random variable, okay, where it's the number of successes in n trials, is given there in green. So it's n choose x, okay, multiplied by the probability p to the x multiplied by 1 minus p, sometimes referred to as just q, n minus x. Now, if you want, okay, you can go over that binomial distribution. I'll put up a link up above there. Okay, I'll make the assumption that you're kind of comfortable with it, and I'm going to extend on that. Now, once we have the binomial distribution, okay, it's sometimes convenient to be able to approximate it by the normal distribution, because we know quite a lot about the normal distribution. So the normal distribution, we can relate it back to z-scores, so bringing it back to a mean of 0 and a standard deviation of 1. We have nice tables of finding out what the probabilities are. Okay, so under a particular interval, we can use various tools, and then we can also use just the normal distribution, so we know what kind of percentage, what the probability is, okay, of our data set to fall within 1 standard deviation, 2 standard deviations, and 3 standard deviations. So all of that is nicely captured, and we can use that to approximate the binomial distribution. Now, there are some assumptions that we're going to make. Most of the time, if you're approximating the binomial distribution by the normal distribution, then you want the number of trials to be rather large. And large is, of course, dependent. Is 10 large? Is 100 large? Is 1,000 large? Okay, so that all depends how much of an accuracy you want to have. Now, if you start getting into 100, 1,000, okay, and so on, you're pretty fair to be able to assume that your normal distribution will approximate, okay, binomial distribution relatively closely. Okay, it won't be exact, but it will be pretty close. So I just want to kind of go back with here and then talk about a few items with respect to the binomial distribution, and then how we're going to approximate it with regards to the normal distribution. So if you recall the normal distribution, we need kind of what the mean is, and then what the standard deviation is. Now, we can assume that we're talking about a population, but of course it's most of the time just a sample, okay, that we might have. So now, with regards to that, for the binomial distribution, if you wanted to find out, okay, and you may recall the expected value really is just a weighted average, okay, that we are calculating, and that weighted average, that expected value, is actually your mean, okay, so your average that you are to expect. And this, okay, I have shown actually in a video, is nothing else but n, which is the number of trials that you have, multiplied by your probability p. Okay, so that is p, where p stands for, okay, the possibility of your success in each individual trial. So I can put up a link up above there. So I've derived that. Now, one thing I didn't derive, but something that we do need, because we do need the standard deviation. And there is a way to find out what the standard deviation is for the binomial distribution, although it is discrete. We have just thought of kind of standard deviation, or at least recently, for the normal distribution, but you can find that standard deviation for any sample set, right? So any data set that you have. So that includes also your binomial distribution. And that has, okay, actually been shown. So I'm not going to go through the detail of showing this. I mean, maybe somebody in the comment one day will put up that they would want to see it. I'm sure you can find it on the web, and people have done it. But if somebody bugs me, I guess maybe one day I'll try to derive it for you. But I'll spare you the derivation at the moment. So the variance, okay, which we designate as sigma squared here, okay, it is equal to the summation, okay, across all your kind of sample set that we have. So if you may recall, so this would have been x minus your mean, okay, squared. And that shouldn't surprise you. Now, the only thing is that because we're talking about binomial distribution, so we have these random variables now, they come at a probability. So actually, this is multiplied, okay, by your probability at that x. Okay, so once you have that, you can sum up across, you know, all the different squares that you have there. Now, the mu, which is your mean, okay, we know, and then we can find each data point that we have, and we can figure out the probability. So the probability is right here. Now, this can be simplified, and it actually comes out to something really nice. It comes out to n times p, which is, again, your mean, multiplied by 1 minus p, right? Or sometimes referred to as q. And that is actually your variance. So that is an equation that we have. And as you know, so if you wanted to know what the standard deviation is, then that would have been just the square root of your variance. So that would have been square root of np 1 minus p. So now that we know what the mean is, and we know what the standard deviation is, okay, right here, under certain circumstances, we can use these two, okay, within our normal distribution to approximate the binomial distribution. So I just want to show you what happens. So with the binomial distribution, I'm going to bring up Desmos because Desmos has the function. Of course, you can do it on your graphing calculators as well. So I just want to show you. So here's Desmos. Now I'm going to put these in here. So n, which is the number of trials that we have. So let's stick to, 100 at the moment. I said it's worthwhile if you're going to be approximating, okay, to have the number of trials to be rather large, okay? So that's 1. Now, the other thing is we need our probability p. So our probability p, well, let's just stick to 0.5 now. So it's almost like, let's say we were flipping coins and tails, right? So, sorry, heads and tails. So the probability is 0.5, let's say if you were hoping for a heads, in terms of having a success. But this can be anything, and then I'll show you an example with respect to that. Okay, so that's my p. So now, if I want to know what my mu is, so I'm going to just put u, so this would be my mean. So this is just n multiplied by p. And of course it's 50, right? 0.5 times 100 would have been 50. Okay, so now what does that mean? That it means that if you have 100 trials, and the probability is 50%, then it should make sense that on average, out of that 100 trials, you will have 50, okay, successes that you would have. If p was, let's say, 0.3 or 30%, then it should make sense to you that you would have 30 out of those 100 trials that would have been a success. That's what the binomial distribution tells us. So now that I have this, so my standard deviation, so I'll just put s, okay, so for the standard deviation, it's equal to, so I'm going to put square root, okay, so that's what we have there. You can pull it up, okay, as you can see there below, right? So we have it there. So that's square root of np multiplied by 1 minus p, all right? And this is s is equal to 5. So that means that my standard deviation is going to be 5. So now let's think about that. If we were trying to approximate this by the normal distribution, what this means is that, okay, so I have a mean, right, at 50, and one standard deviation is 5. So that means from that 50, so from 45 to 55, I have approximately 68% of my data, right, that would fall within there, okay, or 68% probability that I fall within one standard deviation. Now, in terms of binomial distribution, I didn't do this as much when I was doing the discrete random variables, but I do want to tell you, okay, so that you do have, so within your functions under decimals, so if you pull them up, okay, you will have, so in terms of distributions, you do have the binomial distribution. So that is right there. And what it asks for is, okay, so how many trials did you have? Well, we had n trials. And then what's the probability? So our probability is P. And it beautifully maps it out for us. So as you can see here, it maps out the actual distribution across. So of course it's going to peak at 50 because that's our mean. And then it's going to tailor off. And remember what this means for the binomial distribution. So it means that, let's say if x was equal to 0, so that means, you know, what's the probability that you have 0 successes, right, that you would have across, okay, your 100 trials. So that would have been minuscule, you know, that's why you can see it that it's tailing off. And then it starts to pick up, okay, you know, what's the probability of having, let's say, 40, right? So in terms of 40, you know, the probability is not very big. It's about 1% that you would actually have. And then it just picks up. And then the highest probability is, of course, okay, if you have 50 right there. Now, so that's our binomial distribution. This is what it looks like. And it was discrete. That's why it has the points. Okay, so you can map it in different ways. You can, of course, map it, okay, in terms of our function. So this function right here. So you can map it in this way. So you can do this. You can input this function into your decimals, right? And then set it for any x, right? And then map it out. Or you can do it in this way, which does that for you automatically. So that's what I wanted to show you here. Now, this of course looks very close to a binomial, okay? Sorry, into a normal distribution. But normal distribution is assuming that it's continuous, right? So continuous means that it would have to join all of it. Now, it actually doesn't make sense for us to say that it's continuous because binomial distributions, either you have a success or you don't have a success. So how many successes do you have? And so you can't say, you know, what's the probability of having 5.5 successes, right? Or 50.5 successes. But in the normal distribution, that made sense because a random variable was continuous. So it took on values. But here, what we're saying is we're trying to approximate. Okay, and I'll show you an example and then see how it approximates it. Now, in terms of my normal distribution, so normal distribution, so again, decimals has the function for that. And we've done that on numerous occasions. You know, I've introduced normal distribution, you know, put up a link up above there. But if you got to this video, assuming that you already know the normal distribution. So for a normal distribution, okay, so this, I'm going to just type it out in here. I'm not going to look at it up under the functions, but you can. So what is our mean? Well, our mean here is u, okay, which is n times p, and then our standard deviation is s. And notice what has just happened when I did that. Notice that it mapped it up exactly with the binomial distribution, right? As you can see there. And notice how beautiful that bell curve actually looks like. So yes, of course, we can indeed approximate the binomial distribution by this normal distribution. Okay, so these two, but they won't match up exactly when we start calculating probabilities because of the fact that, you know, one is continuous and then one is discrete. And the other part that you have to be careful with, notice that this very nicely maps it out. But if n is very small, right, you'll notice that it won't map out exactly. Like if n was only 2, and I tried to put this in here. Okay, so this would have been, so notice that this is what I would have had. Okay, so if n was 2, I'm going to try to see if I can zoom it out in there. All right, so here it is. It's kind of zoomed out. So this is for n equals 2. So notice, now it doesn't really approximate it that well, right? Because we don't have many trials. Now, if n, even if it was 10, okay, so now it gets, it certainly has gotten better, but it's still not exactly. Notice those points are not exactly on, but it is starting to get better. Now, the other problem is, even if it is something large, as we had originally, so even if we had something like this, right, okay, where it does map it pretty well, I just want to show you, okay, if the probability is, okay, very small, so let's say if I put it at 0.1, notice that I'm shifting it, right, on the fringes to the left, and then my normal distribution is not exactly going to start to approximate it too well. So you have to be careful when you use this approximation. And so for this, so notice that if probability was actually 0.01, notice then it would make no sense actually to try to approximate it, because the normal distribution spans into the negatives. But clearly, you're not going to have negative results for your binomial distribution. So on the fringes, you have to be careful. This, of course, also would have been a problem if I put something like this. Okay, so if I went all the way on the other side, so it would span it out. And of course, because the mean, right, is 99, so it shifts the probabilities on the right, and the ones on the left, okay, have very low probabilities in terms of the binomial distribution. So again, it doesn't approximate it very well, but it does do a pretty decent job, right, if you start doing it and it's not necessarily on the fringes from the left and to the right, right? So within these, we can certainly approximate these. Now, for both of these, you'll notice on the left-hand side, so for the binomial distributions and the normal distribution, it has a cumulative probability. So it can actually sum up for you what the probabilities are. So I just want to show you how closely it actually matches up. So notice for the binomial distribution, so the cumulative probabilities, let's say between 0, so 0 successes, and let's say 40 successes. Notice the probability is tiny, okay? Now this, it's so small, it's practically 0, okay? So this is what you see in there, and it's starting to map it out. Let me maybe shift the probability to 0.5, so that we can actually see this in action. And notice it's highlighting, so it's putting the points in there, right? So from 40 to the left. Now the normal distribution, so here it's 0.0284, that's the probability. So about 3% probability that it's 40 or less. Now in the normal distribution, we said we would want to try to see if it approximated. So if I put 40, now you can technically shift it to 40.5, right? Because it sways it in between. But you can also put it at 40. I'm going to put it at, let's say 40.5, okay? Because of the fact that now it's a continuous, okay, random variable on the normal distribution side. So if you want it at a particular 40, you swing it over, okay, by a half. Right? So now notice these, okay, so it's about 3% as well. It's not exactly, okay, the same as the binomial distribution, but it approximates it pretty well. So, like what if I put it here, and this would have been 50, okay? And then so here, what we would have put in here, so it would have been, let's say 50.5, right? So just a touch over. All right, so that's because of we can round it off. So if the 50 is 50.5, if I just put it at 50, it won't approximate it exactly as well. So now notice these are relatively close. Are they always going to be this close? No. It again depends on the number of trials that you have. Okay, it depends what that probability is. So you have to be careful. Where are you on? Are you on these further out fringes? Okay, where the normal distribution really won't work very well for approximating the binomial distribution. So be careful with that. So coming back, right, where would you possibly use this without, in terms of approximating? So I want to just give you an example where we can do this, and then we're going to compare both the binomial, probability, so we're going to sum up the probabilities, and then we're also going to be doing, the normal distribution as well. And I'm going to do it through decimals. You can do it through z-scores if you like. Again, if you don't have graphing calculators or decimals is not around, that's why it's so much easier to do it than the binomial distribution. Because imagine, let's say just the previous example that I was showing you. So imagine here you wanted to count up the cumulative probability from 0 to 50, right? So you would have to count up, okay, what's the probability of 0 successes, of 1 success, of 2 success? You would have to sum up all of those, doing it individually. Now, doing it individually would have been very difficult for you to do. There's a lot of them that you would count. Imagine you have a lot of trials in there. Now, in terms of the normal distribution, you have a lot of tools to approximate that. And that's why it's so useful. It's the approximation that is useful. Because at the end of the day, nothing exactly is a normal distribution. We would like to approximate our populations, right, that way, or certain characteristics. But those are just probabilities, right? They're not exact. So within here, so like if I would give you an example like this, this is, let's say some other, let's say example, that I'll come up with. So, and to give you some context, so let's say that in a math class, right, I don't know, maybe it's, a tough first year university class, all right, that we have, a total, let's say it's a huge class, right, I don't know, maybe it's at University of Toronto, or maybe it's, somewhere else, in the world, if you're watching it from somewhere. So let's say that we have 500 students. Right, so that's how many enrolled in a math class. And now statistically it's shown, that there's pretty much, so let's say a success rate, so let's say a success rate within that class, of meaning passing the class. Let's say that, on average, let's say 78% of students actually pass the class, which means, 1 minus p. So that would have been, let's say 22% of students would have failed that class. By the way, sometimes it's more than that, So if we have this is really just a binomial distribution. And now what if a teacher, right, or a prof teaching this class wants to know, okay, what's the probability, that I will have, in this case, I don't know, let's say out of 500 students, I would have about, 200 students that would fail. All right. What's the probability of that? So now this teacher is looking at the number of failures, right? Let's say I'm the teacher. So if I'm the teacher, I'm looking at the number of failures. So I could actually swap these two. So my P is actually, so in this case, I'm going to swap them. So this would have been, so I'm going to swap these around. Let's put this, so the probability is 22 because I'm looking for the number of failures. So my success is actually a failure. And then within here, so this would have been actually 78, like this. And I am looking for what the probability is, so my random variable, so I have, at least, 200 failures. So if I want at least 200 failures, that means, so this is going to be something like this, right? So, could have been 200 or 201, 202, and so on. What's the probability of that? Now, this is a binomial distribution, So I can certainly now imagine trying to sum up across the probabilities from 200 and then 201, 202, and so on and so on. Now, of course, we have tools like decimals that can do that for us. But, what I'm going to do here now is I'm going to say, okay, well, what's the mean? So the mean is n times p. So that would have been 500, okay, times p. Now this is percent, so it's going to be 0.22. And my standard deviation, okay, would have been, so that's square root of np, and then 1 minus p right there. So we can substitute all that in here. So 500, 0.22, so it would have been 0.78, and then the square root of that. Okay, so whatever that will be. So we can plug that in here. So square root 500 times 0.22 times 0.78 equals, all right, so it's about 9.26, okay, so on. So now I have my my mean and my standard deviation, okay? So now in terms of approximating this, in terms of my normal distribution, so I can definitely use my z-score, right? So x, minus, and then my mean over my standard deviation, right? And then I can pull up the tables, okay? So this is, okay, my standard tables within here. So whatever that would be in terms of z-scores. So I've done examples with regards to that. I'll put up a link up above there. So I don't have necessarily an interest in using the z-scores, okay, within here because I will be using decimals, all right? But that could have been one particular method. And I certainly don't want to do the binomial distribution. Like I don't want to be, so 200 or more, right, in terms of finding that. I mean, probability of finding the 200 would be fine, which is just one item. But then this is saying, more than that. So I would have to find, the 201, 202, 203, and then find the cumulative summation of all of those all the way up to 500. That would have been a pain. But now doing it in terms of the normal distribution, okay, then that's beautiful because I can actually approximate it and I have a lot of different tools, okay, to use. So here, let me pop up decimals. All right, so from decimals back, so I'm going to just, remove these and put what we just had. So notice my mean, my standard deviation is there. All right, so now I'm going to remove the binomial distribution. And now we are saying, so we want the cumulative probability. So this is from 200. So always, you can put it from 199.5, okay, and above. Okay, so you always put that half, and this is going to be, I guess, to plus infinity. So there we have it. So that would have been, look how tiny that is, right? Super tiny. And I mean, it makes sense because if the failure rate is 0.22, is 22%, and your mean is around 110, and you're looking at above 200, that's all the way at that tail end there. Okay, so pretty much the probability is 0 here. Now, in terms of the binomial distribution, so I'm going to put this one back on, and the minimum I'll put 200, and this is going to be up to a maximum. This is a maximum of n, so let's say 500. And notice it just rounds it to 0, all right? Okay, so that's what you would have had there. So that's the tail end there that you have. And it's so tiny, okay, that it's 0. Now, and that was, I guess, I just randomly put that number in there. But if we wanted to be, let's say, greater failures than 120, right? Or let's say, more than 100, okay, we could have done the same thing. So this would have been from 100, okay, with the probability is about 87%. So let's see if this approximates it much better, 100, so that's 99.5. And look at that. Great approximation on that cumulative, as you see there. So they're both around 87%. So the normal distribution does approximate the binomial distribution relatively well. And you can play around with this. I would encourage you as a student, take this up, put up decimals, or you can use your graphing calculators if your teachers let you do that, and then see the normal distributions versus the binomial distribution and how well they approximate each other. Again, just don't do it on the fringes, Okay, and in fact, I have seen sometimes in textbooks, they'll say you can use the binomial distribution on the assumption that when you have your mean, so n times p, this is going to be actually greater than like 5 or greater than 10. It just depends on which textbook you'll pick up. Okay, let's say by 5. And then they also will tell you, just also check this. Okay, and this should also be, greater than 5. And the reason for that is because you don't want those fringes, okay? You don't want this to be pushed over to either to the left or to the right. That's what I say. I don't say that there's some magic number in here, but I guess in textbooks sometimes they do that. I just say be careful on the fringes, okay? And then since we now have a lot of graphing tools, you can see if it will approximate it well or not, and then you can go from there. All right. Okay, so that is kind of the approximation of your binomial distribution by a normal distribution. All right. Okay, thanks for watching, and I hope that this gave you some insights. Okay, bye everybody.